Hi everyone, I'm Dr. Shane Usher from the University of Melbourne, and I'm going to be talking to you about the Outback Airlock. In 1969, humans landed on the surface of the moon. But in my lifetime, no one has gone beyond low Earth orbit. But in my lifetime, someone will land on the surface of Mars. And as we know, it's a hostile environment beyond Earth's shelter. And my personal mission is to enable an enduring human presence beyond Earth. Right now, of course, most of us are still preparing here on Earth. And NASA has identified 3 areas that are really different that we need to address: radiation, vacuum, and reduced gravity. What we're going to focus on here is vacuum. Now, there are some space analogues here on Earth where people can get exposed to the experience of going on a long-term space mission. As a bunch of Australians, we went to Expedition Boomerang at the Mars Desert Research Station, where we simulated for 28 days what it's like to be on Mars in an isolated camp. Now, of course, this is simulated, so we're not really experiencing low pressure environments. We put on a spacesuit, we jump in the airlock for 5 minutes before we can go outside, but it's all psychological. And there's also a long-term extended isolation mission that Russia runs at the Institute of Biomedical Problems in collaboration with NASA's Human Research Program. And this is a really good system where you have a whole number of chambers, isolation chambers, which have a self-contained environment, and they can do a lot of biomedical experiments here, but they maintain the pressure at just above atmospheric pressure, and you don't really have low pressure environments. They do have an area where you can put spacesuits on and walk around, but it's realistically just the same as the Institute at the Mars Desert Research Station, because it is just that atmospheric pressure. So it's more of a psychological experiment, just again. So just looking at these systems, we have isolation and a confined space, but that's all that we have to simulate a space environment. What I'm proposing with the Outback Airlock is to include isolation and the potential for vacuum to get us used to working with reduced pressure. So I'm proposing a walk-in vacuum chamber. Now, what we can look at here is an area where we have reduced pressure in our everyday lives, or not so everyday for some of us. If we live at altitude, then we have a reduced pressure in the atmosphere and less oxygen to go with it. And in the Tour de France, Alpe d'Huez, this is one of the highest peaks in the Tour de France. That's 3.3 kilometers up, and that has an air pressure not 100 kilopascals, but 67 kilopascals. There's soccer stadiums that are over 3.6 kilometers in altitude, where you have a comparable pressure, only 2/3 of what it is, and the home team has a significant advantage. Everest Base Camp is 5.4 kilometers and only half the regular pressure. At the top of Mount Everest, it's nearly 9 kilometers up and only 30% of the air pressure. Now, if you jump in a plane, the air pressure could get as low as 17 kilopascals outside, but it's maintained to 75 kilopascals or more within the cabin. And there are other examples there. If you cross the Kármán line at 100 kilometers, the pressure is only 0.032 pascals. So that's less than 1,000th of the pressure at atmospheric level. And that's important. And that's really, when you get into space, we need to be able to deal with that, but not just in these spaceships. For the small number of people who've gone on a Virgin Galactic, New Shepard, or Crew Dragon or Soyuz flight to the space station. Of course, we have enhanced pressure as we go down in depth. Scuba divers, aquatic creatures, submarines, and the like experience much higher pressures because the density of water. So just a small depth can double the pressure. At 10 meters down, we've doubled the atmospheric pressure. And that's a lot to deal with. So scuba divers are well equipped to deal with this pressure scenario. Back on land, we have vacuum chambers. And Mount Stromlo in Canberra research facility, they have a vacuum chamber that you can walk into, and you can set up some of your experiments and seal it and depressurize it. But that's really for physics experiments. It's not for maintaining people. Down in the University of Tasmania, the Antarctic Division has built a hyperbaric chamber which can serve some of these purposes. So you can have humans in there and undergo medical research. You can also do other kinds of space type research. And that's a very important facility, but I haven't been able to get there yet with COVID and lockdowns and restrictions, and I'm planning to get there soon. My proposal is to build an Outback airlock. This is an adapted refuse chamber where we can create a facility where people can be exposed to vacuum and reduce pressure environments and make it second nature. Now, to do this, we need this facility to be affordable, transportable, and I'm adapting this from an established refuse chamber design, which is certified to be able to keep miners alive for 36 hours. So if we start with that design, then we can build from there. The most important thing to start incorporating in there is a reduced pressure. And if you have the Outback airlock, you can reduce the pressure and potentially ride a bike up a mountain, play sport at altitude, climb a high mountain, and maybe even take a spacewalk. I'd like to thank my team, which includes Mark Fry, technician, Alexander Reyes, an engineer, Abby, and my graphic designer, who all helped to bring this presentation and this project together. The Outback airlock is, as a concept, is what I have here. We have an antechamber, a vacuum chamber, and a service room. In the antechamber, we have some toilet facilities, but the whole purpose of this chamber is so that someone can walk into there, reduce the pressure, and then enter the vacuum chamber, which might already be at a lower pressure, so that you don't have to lift the pressure in that environment to take people or objects in or out. Of course, we have safety facilities. We need to supply oxygen. Potentially, we need self-contained breathing apparatus. In the vacuum chamber, we certainly need to have food and water and medical supplies. We need communications. And in the service room, we need some form of air conditioning. We will need a battery supply. This is isolated. We'll need a pump to reduce the pressure. We need a CO2 scrubber to ensure that with the extended presence there, you don't have an elevated carbon dioxide concentration. And so if you can spend a day inside out, maybe you can jump on a bike and simulate riding up a mountain. You can spend a day running at altitude, spend a day rowing up high, and now you're ready for a day in space. Or maybe your next job, you're ready. One of the things that we need to do in this chamber is we need to monitor the chamber environment. We need to look at the pressure, the effective altitude that relates to. The oxygen concentration is critical, carbon dioxide concentration, temperature, humidity. And in terms of actual crew members, we need to monitor every person who's in there. We need to monitor their heart rate, you know, what their performance is on the equipment that they're using, how much power they're outputting, how far they've gone. And we also need to continually monitor health, because it's a lot drier in there. So you can sweat more. There's pain to consider, nausea, heart rate, fatigue, and most importantly, hypoxia. If you don't have enough oxygen, you have all sorts of significant health impacts. Applications of this technology, you can use it for training, for confined spaces, altitude acclimatization, exercise training, pilot training, astronaut training. In terms of research, we can research what is going on at altitude, Mars analogues, physics experiments, equipment testing and certification, and spacesuit testing even. Now, where are we at? I have 4 different types of chambers that I'm developing. One is to do it out of a refuge chamber. So this is the budget model that I want to distribute quite widely. I want to adapt a current refuge chamber. I have a large fuel oil tank that I'm currently adapting, and as a test chamber, having a former LPG gas cylinder is just the perfect size to test different pieces of equipment and the like while I get the larger scale equipment up and running. So in terms of process development, I've had to learn a lot of physics, a lot of science, a lot of engineering, a lot of biology, and I've had to look at chamber design, chamber component testing, pressure control, and environmental control, and also health monitoring. And we did a little bit of a test. We connected the pump up to our fuel oil tank and we ran it down. We have a number of different pumps that we can apply. Ideally, we'd go for a more expensive scroll pump, which has no oil vapors that could potentially contaminate the chamber. But I think if we're working for shorter scale, timescale experiments initially, that won't be an issue. But in time, that's what we'll need. Pumping speed, we need to know about pump curves. In the test that we ran, in about 1.5 to 2 hours, we got the pressure down to 25 kilopascals and then sealed it off, not really properly, as you can see down in the bottom corner. We have, it wasn't properly sealed, there were only a few bolts done, but it still took about 4 days to come back to pressure. And one of the key significant lessons there is that the end plate actually cavitated a little. As you can see here with Mark, with his hand twiddling underneath there, that's how much cavitation went on. So as a function of pressure, we have a graph here showing the pressure drop and cavitation length. And that's quite significant. And once all the pressure was gone, it didn't quite return to its shape. So we need some significant reinforcement here. To help with that, we've looked at the design standards. There's no Australian standard. We've looked at the Australian Nuclear Science and Technology Organisation, who run the nuclear reactor in Sydney and the synchrotron in Melbourne. And they have some very conservative design standards. But what we're using is this American Society of Mechanical Engineers boiler and pressure vessel code, which is geared towards vacuum chamber design, at least in part. So we've had a look at some of the reinforcement that's required. This is what's the reinforcement that is on the inside of that chamber at the moment. We need to step that up quite significantly, and we have some preliminary designs which we have to work through. We've also bought some ship doors for access, so doors and hatches, and the idea here is that these can withstand 10 metres head of water pressure, which is equivalent to 1 atmosphere. And they have to be sealed with a special rubber, which is the fluoropolymer trademarked as Viton, which doesn't dry out when you have long exposure to vacuum. We also need to monitor the composition of the air. What we have in that top right-hand corner is a mass spectrometer, which I've purchased, which will be able to monitor all of the compounds. But for a cheaper, more robust system that is more readily accessible, we're looking at pressure sensors and personal gas monitors and how they behave at reduced pressures, and what we need to do to correct the signals, because they might be looking at total pressures or they might be looking at partial pressures, and we need to understand how they work and their limits of performance. Pressure relief valves are also very important, because we want to make sure that the pressure doesn't get too high and that the pressure doesn't get too low. And also we want to ensure that when we normalize the pressure after we've reduced the pressure, that it comes back at an acceptable rate that doesn't burst our eardrums. So I'd like to thank everyone for listening in on this presentation. And I hope to discuss this with you soon.